one of the things that I think we'll do is we'll let you use maximum, all right? So, you know, the computers will be on. If you can go over and just use that on YouTube. You know, you don't have to print out the results, but if you need any results, you could just, you know, use maximum, get the results, and then on a piece of paper say, okay, I found such and such by using maximum. Okay?
So what's going to be on the test again?
So the test, the only thing that's not, it's going to be everything since the last exam.
Yeah.
But what I will not emphasize and I will not put on there are things like, now you have me on video, so, are the wave packet. You know, the free space solutions to Schrodinger's equation, constructing a wave packet.
What are you going to do?
So we're going to start from finite square wheel and up to,
Yeah, yeah.
Finite square well, and then,
The finite cubic well, right?
Yeah.
Yeah. The infinite.
Oh, hold on. You asked us to do Schrodinger equation in 3 dimensions as a homework.
Yeah.
So we should expect that.
Yeah. Yeah, very definitely. So all the things, the side homeworks that I've given you in class, that's all very neat.
That might take like 2 hours to do though.
Well, you know, you should be able to do it and understand it.
Yeah.
Okay? All right, everybody okay? And then it will cover the stuff I finished today as well.
That's all the stuff we do today.
Yeah.
I like how you did the last test. I can just use that test as my notes.
Yeah, that's how.
It's
So that's
a review of that.
Yeah, so I try to make the test an experience, not just spit back something. And, you know, that's what I try
It was
to
an experience, all right.
Yeah. All right. Well, you're using the notes from when you did it again, right? Yeah. All right. So, any big questions then?
This is going to be a lot of matrix formulas and stuff.
I mean, I think so. That's what we've been doing.
Eigenvectors and eigenfunctions.
Yeah, that's what we've been doing, for sure.
Just have one quick thing to ask. It's about 416.
Uh-huh.
Yeah, it's just, were they treating when you started getting a bunch, like Z was the number of protons on that? And were they treating that like a non-relativistic point charge where it's just increasing in magnitude by the number of protons?
You can take a look. Yeah, so that is like what we're trying to do as part of like hydrogen-like systems.
Right.
And so really the only thing that changes in all those problems, so 416 deals with taking, say, like a helium nucleus, right?
Mm-hmm.
And then ionizing one of the electrons. Okay, so then you end up with a helium nucleus and 1 electron.
Right.
So what we say is that's hydrogen-like.
Right.
So when you
Because
go...
it's a 2-particle system. They're calling it essentially a 2-particle system.
Yeah.
So that means they're treating the proton-neutron mass as like a 1, because there's 2 protons in there, so they're just treating it as really one double magnitude.
Okay, well let's make it cleaner than that. When we solve for hydrogen atom, what are we solving the wave function for? The whole atom? When we write down the kinetic energy and the potential energy, what are we writing the kinetic and potential energy for?
The electron.
The electron.
Potential.
Right? The electron?
Yeah.
Do we ever include the mass of the nucleus?
No, I'm not saying the mass, I'm saying the charge. Because
Okay,
that
so
potential pertains to the charge. It's an E squared because you have the E from the electron and E from the proton.
So my point is, when you write down Schrodinger's equation for anything hydrogen-like, it's a nucleus and some electron.
Oh.
All right, and so does the kinetic energy change
No.
of the electron, the functional form or the operator form of it? No,
No,
right?
so
It
it's-
stays the same.
Yeah, 'cause it's
So the
only
only thing that changes is, like you said,
the magnitude of the charge at the center.
right? And so what does that change in Schrodinger's equation? The potential, right?
Right.
So what is the potential in that problem? So instead of the potential for hydrogen is minus E squared, K E squared over R.
Mm-hmm.
Now you have like 2 electrons.
2 electrons.
I mean, not 2 electrons, like that.
So what's the answer
2
then?
protons.
So I'll give you a variable. So let's call,
So like, I drew diagrams,
good,
and I was actually, like, like the solution's posted, but I was like, actually looking at the solution and then comparing to my
you
diagram.
have to work on both. Let's do the problem like this. Here's a hydrogen, and here's an electron, all right? And let's say instead that our potential equals K ZE times the electron over R, where what is Z?
Number
This
of
is the
protons.
normal, this is the normal notation.
It's the number of protons.
It's the charge, the positive charge of the nucleus, right? So when it's hydrogen, and then it's minus right here, when it's hydrogen, Z is 1, so this becomes minus KE squared over R, right? If I want to generalize this to a hydrogen-like system, then I just leave the Z in there, and if it's helium in particular, what I put for, what is the Z for helium?
Two.
Two, yeah.
Protons.
So that problem is kind of like generalizing this problem, just leaving the Z here and see where that factors into the energy.
And just even go more based on that, though, going back to the picture, because I have a Z equals 1, Z equals 2, and Z equals 3 picture. So would you have 2 protons in the center, right, from helium? Would be 2 pluses in the center, so
Yes.
really that Z is just pertaining to, like, it's just magnitude of positive charge in the center.
So we're doing quantum physics at the level that says the nucleus is a little tiny ball of charge.
All right.
I don't see anything inside of it right here. It's just a little
Yeah.
ball of
The
charge.
distance between the two protons is essentially, they're both parallel to the electron.
Yeah, I know nothing
Is
about
there
the
huge?
nucleus
So
other
like,
than it's
like
plus
3
2.
a.m.
There's
I'm gonna
one
make the
radius,
end,
not two, you don't have 2 protons, each of them individual.
It doesn't even
all
care,
one.
it has nothing to do with it, it just says I see a plus 2.
Right.
but- all right.
That's the level that this atomic physics is done. All right, you can go higher, I mean,
Yeah,
but you usually treat that in what's called perturbation theory.
right.
Because this is so overwhelmingly the first order, big chunk of the answer, this view,
Mhm.
right? That you always start here.
All right.
And then if you want to figure out what's going on with the electron actually interacting with the stuff inside the nucleus, then you treat that as a perturbation to that big chunk of energy.
Yeah, it's just when I was looking at the electric potential in my E&M book, in the Berkeley E&M book, it was Q1 over radius R1, R3 plus Q2. Like you had the different radii going to each of them.
Oh, yeah,
So you know,
no,
so I was like, so basically, my question was, is that what they did? They
Yeah.
just assumed that the nucleus they're treating as a point
Yeah.
charge, and then it's increasing by magnitude
That's
the
it.
number of
Yeah,
protons. All right.
yeah, I see, you were making a
Non-relativistic.
molecule. You were making an H2
Yeah.
plus molecule.
Well, I mean, if we're like, and then because they
So
said
they,
later on, talk
I
about-
never, nobody has ever treated an atomic system with 2 radii to 2 protons.
Yeah,
What
the
you
radii,
read.
but so it would come into like
You were reading for H2 plus molecule.
yeah.
You were not reading for, so do you see the
For
difference?
HE
Yeah.
plus.
You were solving this problem. Here's a plus, and then here's an electron.
No. I was doing the pluses were together, but you'd have to actually calculate. Well, yeah, and then when you bring the 2 pluses closer together, the radii would be like an angstrom.
Yeah, it goes away. So
Oh, okay.
you're really
Alright.
you're starting out with a molecule and then trying to build a nucleus.
Ah, okay,
Yeah.
gotcha.
All right.
Which is what the sun already does for you.
Good answer.
Alright.
All right. But good thinking about it. I hope everybody thought hard about that problem too. All right.
Fun.
So does that clear that up, Matt?
Yeah,
Okay, cool. And so then that problem is just how does the energy change? And it changes in a very simple way.
yeah.
All right, and you can figure it out.
Yeah, you can see the number propagates right through the differential solution.
There you go. So if you put in the effort and you put in that, it means a lot. All right, so now I could say, Matt, if you have that answer, look, the ionization energy for a hydrogen electron is minus 13.6 eV. You have to put in 13.6 in eV to change it. That's the energy one. All right, and we know that goes like something over n squared, minus 13.6 over n squared. If you did this problem and saw how that z propagated, then all you're doing is taking that original number, minus 13.6 over n squared, and maybe multiplying it times z. So therefore, let's say that I think it propagates linearly, so it goes with z, or is it z squared?
Z was Z squared.
Okay, with z squared.
Yeah. because it's-
So then, in other words, you've got this great result that the energy levels of hydrogen-like atoms goes like minus 13.6 z squared over n squared. right? So then I could ask you, and
It's just z times e squared, so the z isn't squared, just the e is, so it's just z. It is linear.
No, it's,
it might come
It's-
out.
The book says here that,
and if you look at the solution, it's
Let's see.
inside because it propagates through the whole thing.
Yeah,
There's some square roots, and I haven't done it in a while, but I think it's z squared.
Yeah,
Let's say
it
it's
is-
z
it is
squared
z
over
squared.
n squared. And then I said, what's the ionization energy of the one electron in helium?
One electron.
like 13.6 E squared.
So what is z?
Times times
That's
two
the
times four.
combining.
So it's 13 times 4, so 52 eV. All right, you go and look in a book, and whoa, guess what? The ionization energy to take out the 1s electron in helium is about 50-something eV. All right, it's a very powerful thing.
It's cool.
All right, and I'll take it a step further. Most of the atoms people deal with today, with like cooling and trapping and building Bose-Einstein condensates, are hydrogen-like. All right, and they're hydrogen-like in this sense. Like most people will work with like lithium. All right, and lithium is a 1s squared 2s. All right, and if you look at that, that's like here's lithium as a +3. And then you have in here the 1s squared shell, all right? And then out here you have the 2s, all right? To some level approximation,
Yeah, that's a,
this is approximately a 2s electron going around to some level of approximation, and it's an electron going around the z, what you call effective. Where at some level, what is approximately z effective?
3e.
3. So what does this electron see?
You see a point charge of magnitude 3.
Well, so here's what it is. If you're way out here, and this is an approximation, right?
well, it's so far out it sees the 2 electrons and the nucleus as one mass.
One thing.
So it's just a +1.
So z effective is about 1. And what you say, that's kind of like the screened charge or the shielded charge. To some level of approximation, this 2s electron is looking in, and it's really not seeing the full z of +3, because inside of the 2s,
It's seeing
It's a
a
1s squared.
stable completed shell, so it
Yeah.
treats that stable
Yeah, it's
completed
shielded.
shell as
it's
just a,
shielding. Yeah.
as a 1.
Yeah, and we did this before when we did the Stern Gerlach with silver and some other things. We treated it as just a 5s electron. And people for building Bose-Einstein condensates, they do it with lithium, you do it with rubidium, and a bunch of other cesium and stuff like that. And what you do is look for shells that are kind of filled with just a single electron out there. And those are hydrogen-like. And then once they're hydrogen-like, they're very easy to do calculations. Right? The calculations are only approximate in their first order, but they give you a handle on the problem and they get you something.
Yeah, but you only need to be so close to actually engineer something.
Sometimes, yes. But that gives you a handle. All right, and that's like an effective charge. All right? So good question, good discussion. All right, and then right away you can think of what atoms do physicists like to goof around with in terms of the periodic table?
Hydrogen. Everything on the left.
Okay, everything on the left are the group 1s, right? So the group 1s have how many? They're the first electron outside a closed shell. So the group 1s are very good, but they're also a pain in the neck because some of them are highly reactive. All right, and so you have to be careful, but theoretically, those are the easiest ones to get a whole handle of. So, all right, cool. Yeah, most definitely, like in my lab, I do rubidium, and that's rubidium was the first one, which is it's hydrogen-like. Okay, so let's continue. We'd like to finish this chapter that we're on, which is chapter 4. And here's what we did. Last time, we considered the commutation relations of angular momentum. And what did we find out for the commutation relations of the 3 components of angular momentum?
that L squared and L in any one of the different directions, either X, Y, or Z, you can get but you can't get all three of them.